Hi there, and welcome to today's class. For this class, we'll consider the application of permutation. Last class, we discussed about the introduction to permutation. We look at the algebra of permutation, and we look at how to solve some problems on permutation. For this class, let's look at the concept of application of permutation. Basically, there are three ways we can apply permutation, right? Three basic way. So I'll give you the basic way and show you how it works, right? So let's start with this application of permutation. There are three distinct way to which we can apply permutation. The first one there is called the um, arrangement of distinct objects. Number one, we have the arrangement of distinct object. So your first application of permutation is simply number one, the arrangement of distinct object. The second application, number two, the second application is simply the arrangement of repeated object. So the second application of permutation is simply the arrangement of repeated object. Finally, we look at the third one called the circular permutation. So it becomes your third application of permutation. So note that there are three ways to which we can apply for permutation. The first one there is called the arrangement of distinct objects. Second one there is called the arrangement of repeated objects, while the third one is called the circular permutation. We look at these three applications one after the other. So the first one there called the arrangement of distinct objects. Arrangement of distinct object. So what's the concept behind arrangement of distinct object? So please, very important, please note this, very important, please note it's very important. When it comes to arrangement of distinct object, the objects given are not repeated. That's the concept. When it comes to arrangement of distinct object, the objects that are given are not repeated, right? So what do I mean? We'll take some free problems and we'll stress this point. So when it comes to arrangement of distinct object, the objects that are given are not usually repeated, are not even usually, are not repeated. That's the concept. So let's explain the idea behind this first concept with some example to further buttress this point. Example 1 says, in how many ways can the letter of the word be arranged? Number one there. In how many ways can the letter of the word be arranged? Number one there, I have Lagos. B, I have Lasting. And C, I have this. All right, look at it, please. They said the question says, in how many ways can the word be arranged? By the way, when you hear the word arrangement, we said last class when we discussed about the introduction to permutation, we said permutation actually deals with what? The word arrangement. So when you hear the word arrangement, don't stress, it's just permutation. So I mean the word, in how many ways can these three words here be arranged? So what do I do? Now, why is it that this example is explaining the first application called arrangement of distinct objects? For distinct objects, observe this object, they are not repeated. This is Lagos. Nothing is repeated here. Observe your two, Lasting. Non-object is repeated here. Look at this one, Cape. Nothing is repeated. So the concept now is that look at this one. If I have, let's say for example, Abuja, look at this Abuja for God's sake. I'm having A and A. There are two objects repeated here. So you can apply the way you solve this will be different from the way you solve non-repeated. So when it comes to the first application, and of this object, the object there are not repeated. So how do you solve it? So the way you solve this one will be different from the way you solve when it's repeated. So that this one becomes your second application, repeated object. Let's solve this please together and let's see what we get. For number one there, solution number one there, I have Lagos. I have Lagos. So how do you solve this? So far, observe that the objects here are not repeated. It's quite simple. Just count total number of objects. This is 1, 2, 3, 4, 5. That becomes a 5 factorial. That becomes 5 factorial, which is equal to what? That's 120. 120 ways. Listen up. That is quite simple. When the objects are not repeated, what's your task? Just count total number of objects there. That becomes yes 1, 2, 3, 4, 5. That's 5 factorial. So then that is 120. That's all. Let's do number 2 and C. For B there, I'm given last thing. We said so far the objects here are not repeated. What do? Count them. 1, 2, 3, 4, 5, 6, 7. That becomes a 7 factorial. I have 7, which will give what there? 5040 ways. So I have this. It becomes my answer to that question. Next up, the last one here is saying C. For C there, I have C A P E. Objects here are not repeated. What do you do? You just count them. So what do I get? That's 4 factorial, which is what? 24 ways. So the question says, in how many ways can the word be arranged? Lagos can be arranged how many ways? 120 ways. Latin, that's 5040 ways. Cape, perhaps Cape, yes, that's 24 ways. This becomes how to solve problems under the first application called the arrangement of distinct objects. So you should know when I see a question, you should know that this question is under arrangement of repeated objects or distinct objects. For distinct objects, the objects are not repeated, right? That becomes your task. Let's take one more question under application of distinct objects, then move to the second application. Example 2 says that in how many ways can the word boy girl be arranged such that BGI must be together? Very easy. So the question number 2 says that, number 2 question, example 2 says that in how many ways can the word boy girl be arranged in how many ways can the word boy girl be arranged such that BGI must be together. Let's solve this problem here. Observe that the word given is boy girl. In this boy girl here, there is no repeated object there. That becomes a condition under what? The first application. Now listen up. How do you solve this one? It's quite simple task. This one says, in how many ways can the word boy girl be arranged such that BGI must be together? There's a condition here. Let's solve this please. Solution. We are told that BGI must be together So I'm given the word BOYGIRL, boy girl, from the question. But the question says that let BGI be together. If I pick up B, G and I, I'm left with what? O, Y, R, and L. Observe, please. The question says, in how many ways can the word boy girl be arranged such that BGI must be together? So if BGI must be together, I'll have something of this nature. So in how many ways can the word be arranged? Now, how do you solve this one at this point? Your first task is that consider the term that must be together first. So this is 1, 2, 3. That becomes a 3 factorial. Are you seeing that? Consider this one first. Times, you consider this bracket here as 1. Listen up. We said consider the term that must be together first. That's 1, 2, 3. That's 3 factorial. When you are done, we will consider everything here as being 1. All the term here as being 1. That becomes 1, 2, 3, 4, 5. That becomes a 5 factorial. At this point, if I multiply 3 factorial by 5 factorial there, I'll have 720 ways. So it becomes how to solve this particular problem. Your task is simple. Count out the number that must be together, the object that must be together. That's 1, 2, 3. That's 3 factorial. When you are done, this is 1, 2, 3, 4. Consider the 10 that will be together as one thing. That becomes 1, 2, 3, 4, 5. That becomes factorial. Multiply them, you have this answer. It becomes how to solve this particular problem using the concept of what's it called? Arrangement of distinct objects. Let's do the second application called the arrangement of repeated objects. Number 2 there, we have the arrangement of repeated objects. Arrangement of repeated object. Let's do the second application called the arrangement of repeated object. So when it comes to this concept, the task is quite simple and easy. Observe that I just explained this concept using Abuja for you, right? The task now is that the object in when it comes to the second application, the object there are repeated, please. So I'm saying that when it comes to the application of repeated object, the objects are repeated. Let me use this. Let me explain this using some example to explain this concept. Then we're off. Example 1 under this. One says, in how many ways can the following word be arranged? Question A there, I have Abuja. Question B, I have access. Question C there, I have economy. And finally D, I have accountant. All right, let's solve this problem. Mind you, observe the reference from your first one and your second one. For this one here, objects are not repeated. How do you solve it? Just count them and you are off. That's all, right? For this one now, is different. The way you solve it is different. So how do you solve something repeated in this pattern? How do you solve it? Look up, please. Solution. To solve this is a quite simple task. What's the task there? Start with number 1 there. I have Abuja. Please, the same techniques applies too. What do you do first? Count total number here. This 1, 2, 3, 4, 5. That becomes a 5 factorial. All over, please. All over, how many objects are repeated here? How many? I'm having A, B, J, and A, B, U, J. But A occur 2 times. That becomes 2 factorial. Let's say, for instance, B occur 2 times 2. That becomes times 2 factorial. I say that let's assume that B2 occur 2 times because what a 2 factorial again. But in this case, it was just A that occur 2 times. That becomes a 2 factorial for A alone. So I said A, nothing occur again. So that I'm stopping at 2 factorial. So I will have this one here. So it's my tax now is quite simple. What's 5 factorial? That's 120. All over 2 factorial is what? Is 2. If I divide the 2 of them, I'll have 60 ways. So it becomes your answer after solving that particular problem. Let's do number 2. For B, I have access. For access, how do you solve it? Observe that they are repeated. So its tax is quite simple. Count the number first. Count the number. So I have 1, 2, 3, 4, 5, 6. That becomes a 6 factorial all over. Check. A is not repeated. But C 2 times. For C alone, I have 2 factorial times S2 is repeated 2 times. That becomes a 2 factorial. Aside that, E is just once and A is 1. So I'll stop at this point here. What I get here is equal to 6 factorial all over. I'll have, this is 4. This will give 4. What will be the value for 6 factorial? So if I divide 6 factorial by 4, I'll have about 180 ways as being my answer to that particular question. Observe the way I just differentiated the first application and the second one, right? Let's do economy and you do accountancy for me and put your answer in the comment section. I'll reply you as fast as I can. For the last one, let's do economics. So we said first things first, count the number 1, observe 1, 2, 3, 4, 5, 6, 7, 8, 9. That becomes a 9 factorial all over. Check how many objects here are repeated. That's your tax. From here now, I'm seeing that O occur 2 times. That becomes a 2 factorial. I have picked O and O. Aside that, I can see that C occur 2 times too. Look at C and C. So I have C and C. That's just 2 times 2 factorial. As I see, is there another object here that repeated? Of course, no. So I have this here. So it becomes a 9 factorial all over what? 4. If I divide 9 factorial by 4, I'll have 90720 ways as being my answer. So you try doing D and put your answer in the comment section. I'll reply you as fast as I can. All right, let's do one last example under the application of permutation under the arrangement of repeated objects, and we're off. So we'll do the last one there. So call it a day. All right, let's solve this particular problem under arrangement of repeated objects, and then we'll move to the last application called circular permutation. The example says that in how many ways can the word consonant be arranged such that A, there is no restriction, B, NNN must be together, C, NNN must not be together, D, SOOT must be together, E, SOOT must not be together. How do you solve this? It's a quite easy task. The real word there is consonant, right? The major word there is consonant. So for number example word there, example two, the major word there is sorry. The major word there is consonant, right? So they're telling us that in how many ways, yes, in how many ways can the word this consonant be arranged so that for question A there, I have there is no um restriction. There is no restriction. How do you solve question A? When you hear the word there is no restriction, it means solve it normally. This becomes what? Let's solve this one normally now. Constant normally. What do we mean? Use this concept now, right? Solve this one normally. That's the meaning. Solve it. Let's say let's say that it's among here now. How do you solve it? Just count the total number and then divide it by the number of repeated object there. So there's no restriction means solve it what normally. So I'm having what consonant. Please, you said first is first. Count the number of objects. 1, 2, 3, 4, 5, 6, 7, 8, 9. That becomes 9 factorial all over. Check. How many objects here are repeated? That becomes check very well, please. Observe that OO repeated twice. That becomes a 2 factorial for your OO. Next up, observe that S is how many times? Sorry, N 1, 2, 3. That becomes what? Times what? 3 factorial. Is that all? A just once, T2 is just 1, C is 1. So that's all. So it becomes your tax here. So at this point now, how do we get this? My 9 factorial divided by this will give 30,240 ways. So it becomes my answer. So I have about 30,240 ways. The object can be arranged in 3,240 ways. So that becomes your idea behind no restriction. It means solve it normally. What do you have? You have this. Number 2 question says that n must be together. So for B, I have n, right, must be together. If this must be together, what do we mean? I have picked out n. They said n must be together. I'll be left with what? I have picked this, and this. I'll be left with what? C, O, S, O, A, then T. So I have this left. So if n must be together, I'll have this left. So now we said first is first, consider the term in brackets first. First, I have what? Just 3 elements, 3 objects. That becomes 3 factorial. But mind you, these objects are repeated in 3 times. That becomes over what? Over 3 times. We say consider this one as 1. That becomes 1, 2, 3, 4, 5, 6, 7. That becomes 7 factorial all over. Observe that OO is repeated twice here. So I have all over what the 2 factorial. If we can have to solve this problem here. Mind you, at this point now, I can easily divide 3 by 3 here. So I'll be left with what? Just 7 factorial all over 2 factorial. If I punch this from calculator, what do I get? 7 factorial divided by 2 factorial. I have about, my answer becomes 2520 ways. That becomes my second number, my second answer to that particular question. All right, for 8, I have that A, B. For number question C, question C says that N and N must not be together. Listen up, please. Because one says N and N must not be together. What's the tax? It's simple. Observe that we just look for N must be together, and we had this, Abi. So to get N must not be together, the task is quite simple. Go back to your no restriction value. That becomes what? 30240. Subtract it from must be together. That becomes 2520. If I subtract these two values there, I will have about 30240 minus, how about 27720 ways. So your task now is that if I given to find there is no if I given to find must not be together, you have to look for must be together first, right? And you sort that value from what your no restriction, then you have your value this way. So C says that's C. Let's do question D. This says SOOT must be together, and E says SOOT must not be together. So you try doing that one. Try doing D and E for me using this same pattern, right? I used there. So for your D, SOOT must be together. So you combine SOOT together first, as in this case here. Then you write the other object that are remaining. Then you solve it using the same pattern here. So do D and E for me and put your answer in the comment section. I'll reply you as fast as I can. Or perhaps, all right. Let's do together, please. Let's do together, please. Let's do D. For D, this says SOOT must what? Be together. So if I have SOOT together, if I pick, observe please, I'll pick SOOT. I'm left with what? C N N A. That's what, please. I'll left with CNNA. Okay, CNNAN. Per se AN. So I'll be left with this, please. So observe that I'll be left with this. So let's solve this. What do we get here? This becomes 1, 2, 3, 4. That becomes a 4 factorial all over. Observe that occur 2 times. That becomes over 2 factorial. I'm done with this. Times, we said, count this 1, 2, 3, 4, 5. 5 Abi. Consider this as 1. That becomes a 6 factorial all over. Observe that n occur 3 times. 1, 2, 3. That becomes 3 factorial. Mind you, don't go and say 2 factorial cancel 4 factorial. That becomes 2 factorial. You are wrong. Don't go and say 3 factorial over 6 factorial. That becomes 2 factorial. No, it's wrong. It's wrong. So let's get this value, please. From here, what do we get? All right, what do I get from here? So we know that 4 factorial, perhaps, that will give 24 over 2 times 6 factorial there. That should give about 6 factorial. I have 720 all over 3 factorial there is 6. If I divide 24 by 2, I'll have 12 times, divide 72, 720 by 6 there, I have 120. Multiply that 12 by 120, I have about 1440 ways. So it becomes your answer to question D. Let's do question E. We said for question E says that SOOT must not be together. So we have gotten the tax must be together. So what do we do there? This one says SOOT must not be together. What's the tax? Go back to restriction value. That's 240 minus the value you had here. That was about 1440. So what I get here, that's 30240 minus that value there. I have 28800 waste. So this becomes your answer to that particular question. Let's do the last application and we're off. So the last application there is called the circular permutation. Let's do circular permutation. For circular permutation, it has a formula. What formula there? The formula is given by n minus 1, then a factorial. What does it mean? If I'm given any n value, I must subtract it from 1, then take the factorial of that number. That's all. So let's take an example to further explain the last application. So when you hear the word, how do you possibly identify if a question is talking about the last application called the circular permutation? The way you identify it is that questions do come in this form. Look at this one. It says that in how many ways can 8 be arranged around a circular dining table? Hear the word round. That's circular permutation. So for the circular permutation concept, you get the word round the circular table, revolving round, just hear something round, right? Circular part, something like that. Now that becomes your idea of circular permutation. Let's do this problem. The problem says that in how many ways can 8 be arranged around a circular dining table? That's concept. What's the n there? N is 8. So in that question there, n is given as 8. So we said the formula is that you must subtract that value given by 1 and take factorial of it. That becomes, what's n? That's 8 minus 1, then factorial. That's what? 7 factorial. And 7 factorial will give 50440 ways. So this becomes your tax under the last application called the circular permutation. Just know that whenever I give you any value, maybe 8 or 9 or 10, just subtract that value from 1 and then take the factorial of that number. So you're off. So it becomes your tax. So if you found this class helpful, do it to like, hit the bell icon, subscribe to my channel, share to your friends and classmates so they can learn too. If you're also interested in assisting us, I'll drop my account detail in the description of this video, right? So you can assist us with anything you have. No amount is too small, right? So in order to increase our knowledge and also to make our consistent video easy. So thank you for watching and welcome again to Excellent Link Academy. See you in the next class. Bye.